This problem looks a lot harder than it actually is. We basically want to find the number of ordered pairs a, b, which a and b are integers, that this polynomial has three distinct integer roots. And so let's just look down at what the polynomial actually means. If it has three distinct roots, that means it can be written as x minus p, x minus q, x minus r for three integers p, q, and r that are not equal. These are the roots. And if we actually expand this, we see that this last term is going to be negative p, q, r. So we get negative p, q, r equals 6. Let's just find p, q, and r that multiply to 6. So, well, what multiplies to 6? 1, 1, 6 multiplies to 6. 1, 2, 3 multiplies to 6. And there's not much else right here. But the key fact is that we need to include the negative. The negative needs to be in here somehow. And first of all, if we just do 1, 1, 6, that's not three distinct integers roots, so we need a negative. This is not distinct, so let's just turn it negative 1, 1, 6. These multiply to 6, and that's a perfectly valid combination of roots. Next, 1, 2, 3, let's look at this one. So there needs to be a negative in here somehow. These need to multiply to a negative, so we could have negative 1, 2, 3, we could have 1, negative 2, 3, we could have 1, 2, negative 3, but the trap here is that we could have all three negatives as well, so negative 1, negative 2, negative 3. So these are all the 1, 2, 3, 4, 5 different combinations of different roots, p, q, and r, such that this has three distinct integer roots that multiply to 6. They have to multiply to 6 or else it's not going to be this polynomial. And so these are the 5 different combinations. So each of these combinations is going to create an ordered pair of these, because each of these combinations, if we plug them in for p, q, and r, is going to be some distinct, when we multiply them out, it's going to leave some distinct a and b. They can never be the same. And so because of that, this 1, 2, 3, 4, 5 is our answer.